welcome to the fourth lecture of transportation network analysis. So, in the last lecture we were discussing an optimization formulation for the traveling salesman problem. In that we had seen that there were a set of constraints called subtour elimination constraints, and the number of such constraints could be exponentially high in terms of the size of the problem. And therefore, in this lecture we will be looking at an alternate formulation for the traveling salesman problem. So, in this formulation the subtour elimination constraints have been replaced, and this has been replaced by this person A.W. Tucker. So, this is also called Tucker formulation. So, the objective function of this formulation still remains the same, that is minimizing summation Cij Xij, where the summation is going on the set of all the edges that are present, subject to this first constraint that is there, that for every node j there is exactly one node I from which edge is selected in this tour, and that edge leaves this node I and enters node j. Similarly, for every node I we have exactly one edge ij that leaves this node I and enters node j. So, these two constraints are the same. We are now introducing this new set of constraint in place of the subtour elimination constraints. So, here we have ui minus uj plus n xij less than or equal to n minus 1, and this holds for every pair of nodes I and j, such that nodes I and j will belong from the set 1 till n, so excluding the node 0, and the nodes I and j should not be the same. So, here these variables ui and uj are not restricted to be integers, so they can take any real values. And then we have these constraints that xij is binary, so it can only take the value 0 or 1 for all set of edges I and j. So, we will be discussing this new set of constraints where we have ui minus uj plus nxij less than or equal to n minus 1. So, we will be focusing more on this. So, what we need to argue is that with this new set of constraints, we are not only restricting the solutions to the tours, but we are not excluding any tours. So, what we want is that in the traveling salesman problem, the feasible region should consist of all the tours that can exist. So, it should not exclude any tour, but then we should not be having anything other than the tours. So, the feasible set or the feasible region that is formed by these constraints should exactly be equal to the set of all the tours that are possible for that given graph. So, we will be proving that now. So, the first part that we will be doing is that every feasible solution is a tour. Now, in order to argue this, we show that every circuit passes through node 0. So, why is this important? Remember that the first two set of constraints that we have are already ensuring that for every node there is exactly one incoming link which is selected and one outgoing link that is selected. Okay. So, with those constraints we can get something like this here. For example, if there is this node 1, and suppose this node 0, then there is this node 1, then there is this node 2, then there is this node 3, then node 4, then node 5. And suppose if we just had the first two set of constraints, that is for every node there is exactly one link that is incoming and that is selected in this final solution, and there is exactly one link that is outgoing from this node and that is selected, then we can also get a solution like this here. So, in this solution we have two subtours now. So, there is one subtour that is starting from node 0, then going to node 1, 2 and then back to 0, and then on the right side we have this another subtour that is going from 3 to 4, node 4 to node 5 and then back to node 3. So, these two subtours satisfy that condition. For every node that is there is exactly one incoming link and there is exactly one outgoing link that is selected as part of the solution. Note that in these edges that are shown here, only the edges that are finally selected we have shown. As such, there are many more edges that are present between these in this graph that is shown here. So, for every pair of nodes we are assuming that there is an edge that is present, and one pair of edge is going from node I to node j and another edge is going from node j to node I. So, now this kind of solution where we have two subtours, this is not what we desire. what we want is that there should be some single tour that covers all of these nodes. We do not want these separate small tours, and therefore, if suppose we are able to argue that every solution that you get from these constraints that I showed in the last slide, they will be such that that circuit that comes from that passes through node 0, then we cannot have something like this, because in this right figure here, where we have this subtour which is starting from node 3, then going to node 4, then node 5, and then node 3. So, this one is not passing through node 0. Okay. So, if we argue that every circuit that gets generated from the feasible solution passes through node 0, then we will not be getting any solution like this. So, then we need to have something like this here, where this is node 0, 1, 3, 4, 5, and this is node 2, and then we need to have something like this here, a single tour that passes through node 0 and of course also satisfies the first two set of constraints, that is, for every node there is exactly one incoming link that is selected in this tour and exactly one outgoing link that is selected in this tour. Okay. So, now let us assume that a sequence of nodes I1 till Ik is a circuit that excludes node 0. So, we can now write the inequalities that we have in the new set of constraints as follows. So, since we have nodes I1 till Ik, so we will get this first set of constraints here, where we have uij minus uij plus 1 plus n less than or equal to n minus 1 for all j which is going from 1 till k minus 1. So, for example, if suppose we had nodes I1, I2, I3, okay. So, then for nodes I1, I2, we will be having this equation that u I1 minus u I2 plus n is less than or equal to n minus 1 for all j. So, here this one is the first equation that we will be getting. So, this is the first equation, then we will be getting u I2 minus ui3 plus n less than or equal to n minus 1. But as we go from node I3 to I1, then we will be we cannot write it in this way that we have a node uij minus uij plus 1, because in that case the first node has j that is lesser value than the other one. So, that is why this last constraint where we are going from node I3 to I1, so that needs to be written separately. So, that is why we have this last constraint here. So, we will be having this ui3 minus ui1 plus n less than or equal to n minus 1. So, that is why this last constraint is written separately here. Okay. Now, let us look at the set of conditions here very closely. Now, if we add all of these conditions, what we will be getting is that all of these u's will get cancelled out. So, on the left hand side we will then have only n's, and on the right hand side we will have just n minus 1. So, we will be finally having these inequalities that n times k is less than or equal to k times n minus 1. This is what you will be getting if you add all of these equations here, which definitely is not true. Okay. So, therefore, we arrive at a contradiction here, and since we arrive at a contradiction, our initial assumption that node 0 is not there in this circuit that we have is wrong, and therefore, every feasible solution in this set of constraints will be passing through node 0, and together with the other two constraints that we already had, that for every node I there should be one incoming link and one outgoing link that is part of the tour. We will never get subtours, we will always get single tour that will be passing through all the nodes. Okay. So, in this direction of the proof, we have argued that every feasible solution that we get is a tour. Now, what needs to be argued is that in this process we have not excluded any tour. Okay. So, a way to prove that is, suppose we have this travelling salesman problem given to us, an instance of a travelling salesman problem, and suppose someone comes up with a tour of that. Okay. Now, we want to argue that this tour is part of the feasible region that is formed by these new set of constraints here. That is, there will be some values of u's, xij's for which we will be able to get that tour which is given to us. So, in that way we will be sure that we have not excluded any tour in this set of constraints. So, this is what it is showing, that we now show that for every legitimate tour there are values of ui that satisfy the new constraints. Okay, now in order to prove this, we will be proposing that if you select the values of these variables u in a particular way, then for every tour that someone gives to you, you will be able to find the values of these decision variables u and xij for which these constraint set will be satisfied. So, in that way we will be fully sure that every tour that someone gives you for that given example of the traveling salesman problem, it is possible to represent it mathematically in the set of constraints. So, the way you select the u values is such that you set u0 equal to 0 and ui equal to t if node I is the tth node visited on the tour, where t goes from 1 till n. Okay, now let us see how does it work. So, we have defined a way in which if we select particular set of u values, then we will be able to guarantee that if someone gives you a tour of the traveling salesman problem, then we will be able to find the values of u's and so on that will satisfy the constraint set that we have. Now, since we also have these variables xij in the problem, so there can be two conditions. I mean, sometimes for a particular pair of nodes ij, xij can be 0. Okay. So, suppose xij is equal to 0. So, what we want to prove is that in that case the u values that we select in the particular way that we have proposed, that let us set u0 equal to 0 and ui equal to t if node I is the tth node that is visited. So, if we do that, then we will be getting this constraint here. So, this is the set of new constraints that we had and we have put xij equal to 0. Okay. Now, we need to argue that if we set the u values that we proposed in the last slide, that is for node 0 you set u equal to 0 and for node I that is visited in the tth order in this tour that you give me, then if I set ui equal to t, then this set of constraints will be satisfied, and this will always be the case. Okay, because you can see that what is the largest value that these u values can take. Ui can either take largest value to be n and uj can take maybe as low as 0. In that case the LHS will become n, and only in that case this inequality will not get satisfied. However, that case is not possible here, because the case ui equal to n and uj equal to 0 is ruled out, since it is already said that this set of constraints have I and j such that they only take the values from 1 to n. So, you cannot have a node j that is the same as node 0, and since we have already reserved the u value of 0 for node 0, we cannot have uj equal to 0 here. Okay. So, if uj cannot be 0, then it is an integer value which is greater than 0 and less than or equal to n, and in that case if ui itself is upper bounded by n and uj will be something greater than equal to 1. So, then the difference ui minus uj will never exceed n minus 1. Okay. So, therefore, if you select u values in the way that we propose, that for node 0 set u equal to 0, and if node I is the tth node that is visited in the given tour, then you set ui equal to t. So, then that will be satisfied if for if xij is equal to 0 for node I, if you go from node I to node j, that is there is no edge that is selected if you go from node I to node j. Now, there can be another situation, that suppose you have a pair of nodes here in which the edge that goes from node I to node j is part of the tour that you select. So, in that case xij will be equal to 1. So, in that case we are again writing down this new set of constraints here. Now, it is ui minus uj plus n xij, and xij is equal to 1. So, that is why it is n times 1 here, and this is less than or equal to n minus 1. Now we need to argue that if we set the u values in the way that we proposed in the last slide, that is for node 0 set u equal to 0, and for node I set it equal to t if it is the tth node that is visited in that tour, then this condition will always be satisfied. And we are lucky that this will always satisfy, because see, if xij is equal to 1, what does this mean? That is, the link that goes from node I to node j is part of the tour. Okay. So, in this tour we are going from node I to node j, and the way we have defined the u values is such that node I is the tth node that is visited in this tour, then we set the u value for that node I to be equal to t. So, as you will go further in this tour starting from node 0, the u values will only increase. For example, suppose node A is the 0th node, so for that the u value will be 0. Suppose you, after visiting node A, you go to node D, so for node D the u value will be 1. Suppose after node D you visit node B, so for node B the u value will be equal to 2. Okay. So, you will see that if you have such a pair of nodes from I to j where xij is equal to 1, that is this, that we are going from node I to node j in this tour that is given, then the u value for node j will be exactly 1 greater than the u value of node I. Okay. Only this condition will not be satisfied when you are coming from the last node in this tour to the node 0 from where you started. Okay. But we do not need to worry about that, because uj cannot be equal to 0 for the same reason that we had given before, because here nodes I and j are not allowed to take the value 0. Okay. So, therefore, ui minus uj will always be equal to minus 1. Okay. So, this condition that minus 1 plus n is less than or equal to n minus 1 will always be satisfied. So, therefore, in this way we have argued that if someone gives you a tour of the travelling salesman problem, then there will be a set of variables u's and xij's for which this set of constraints will be satisfied. So, in that way we are not excluding any tour in this set of feasible region. Okay. So, now we will be discussing another set of important optimization problems. It is called a complete matching problem. All of these optimization problems that we have discussed until now, like travelling salesman problem, maximum coverage and so on, knapsack problem. So, all of these are combinatorial optimization problems, because the feasible region in this set of problems is finite. So, we have finite number of solutions and we have to select the best solution or the optimal solution from that. So, complete matching problem is also an example of that. It is a very useful problem because it has wide ranging applications starting from ride sharing to job allocation. For example, if you have a set of customers that need rides and you have a set of taxis, so which taxi should be assigned to which set of customers, so that a particular objective is reached. For example, the total cost that is beared by the taxi company is minimized, or whatever objective that might be useful. Okay. So, this kind of matching problems are useful wherever we have to assign a particular set of items to another set of items. So, in this course we will be discussing a specific kind of matching problem. It is called the complete matching problem. So, let us look at an important kind of graph before discussing this matching problem. So, a bipartite graph is a graph where we first have the set of nodes which is given by V and the set of edges which is given by E here, and here this graph can be divided into two non-empty subsets A and B. Okay. So, whatever the total set of nodes that is there V, so that can be divided into two non-empty subsets A and B, such that every edge in this set E has one endpoint in A and the other endpoint in B. Okay. So, let us take a look at this example here. Here we have two type of nodes. One is the red colored nodes here and the other is the blue colored nodes at the bottom. So, you will see that we only have edges between the top pair of nodes and the bottom pair of nodes. So, you do not see any edge that has both the end nodes as red or has both the end nodes as blue. So, it will always have one end node as red colored node and the other end as the blue colored node. Okay. So, this is an example of a bipartite graph. Okay. So, why is this useful? I mean, you can think that maybe the top set of nodes is representing the set of customers, the bottom set of nodes is representing the taxis that are there. So, we have to do some kind of matching here. So, that is why the only edges that are present are between these two sets A and B that are present here. So, what we will be assuming is that suppose one of the sets of nodes A has size less than or equal to the another set B here, and we are given non-negative cost Cij for every edge that is present in this edge set. Okay. So, a complete matching of A is a subset of the edges M from this set of all the edges E, such that every node in A has exactly one edge of M incident on it, and each node in B has at most one edge of M incident on it. Okay. So, let us see what does this mean here. Okay, let us take an example here. Okay. So, suppose we have these 6 nodes that are present here. The top nodes 1, 2, 3 suppose belong to the set A here, and suppose we have these 7 nodes at the bottom which is represented by the set B. So, set A has number of nodes less than the set B here, and we have some edges that are connecting these some set of nodes in set A to some set of nodes in set B here. So, we have to select, we have to give an example of a complete matching here. Okay. So, suppose I decide to select, suppose this edge, this edge, this edge and this edge. Okay. Now, let us see whether it is a complete matching or not. So, you can see that I have selected 4 edges, one is the edge 1 4, the other is edge 1 5, the other is edge 2 6 and the other is the edge 3 7. So, all the nodes 1, 2 and 3 are such that for the nodes 2 and 3 there is exactly one edge which is incident on it, but for this node 1 here there are 2 edges that are incident to it, 1 4 and 1 5, and therefore, this does not satisfy this definition of complete matching here. Okay. So, therefore, we cannot have these edges 1 4 and 1 5 together. So, let us maybe remove this edge 1 5. Okay. So, now all the 3 nodes 1 2 and 3 are exactly having one edge that is incident on these node and that is selected here. Okay. Now, let us look whether the other condition is satisfied, that for the set of each node in the set B, we have at most one edge that is incident on that node and that is selected. So, for node 4, there is this edge 1 4 that is selected and that is incident on it. For node 5, there is no such edge that is selected and that is incident on it. And for node 6 and 7, there are exactly one edge for each of them that is incident and selected on it. So, that is why this now satisfies the criteria of complete matching. So, this is one example of complete matching. There can be several such cases of multiple of complete matching. So, what is the target here is that out of all of these complete matchings that are possible here, we want to find that complete matching of this problem that has the minimum cost. Minimum cost means that the sum of the cost of the edges that are selected, that is the cost of the edge 1 4 plus the cost of the edge 2 6 plus the cost of the edge 3 7, this should be minimum. Okay, so we want to select that complete matching that has the minimum cost among all the possible complete matchings that are possible. Okay, so we will be continuing this matching problem in the next class. We will be seeing the optimization formulation for this. Thank you.